Now what we're going to do is we're going to take a look at Minitab and try to understand two things. How do we create the design for a full factorial experiment? And then how do we analyze that design? The first video is going to focus on this process of creating a design in Minitab. So what we're going to do is we're going to take a look at a particular design. The data file is called customer complaints. And in there what we're going to see is that from this design that we have, how do we get that into Minitab, and then how do we create it originally in Minitab? There's two different ways that we might take a look at this. So again, we'll begin with the creation process, and then we'll take a look at how do we bring a design into Minitab. And after that, we'll take a look at, in the second video, how do we analyze that after we've conducted the experiment. We're going to take a look at DOE in sort of two of these lessons. In the first one, we'll look at the design of a full factorial. And the second one, what we'll do is we will take a look at the analysis of a full factorial design. Now, we're going to use a data file here, which is called complaints in this. And you'll see this is already listed here. So we see that there's a number of complaints that have been issued. And this is the same data set that was in our module which we talked about DOE. So you'll be able to follow this a little bit, and we've explained the data set there. Now, the idea in setting up a DOE and planning is a very important component, but the Minitab planning is actually relatively easy compared to the physical planning of the DOE. So we go to Stat DOE and Factorial Design. So typically we would begin with Create a Factorial Design. Now, I already have a factorial design in this sheet. So I'm going to work through this to a certain point in time just to be able to illustrate what you do, and then I'm not going to save that design. And the reason is that when we actually go through this, we will input the design here, and then we'll use that for analysis in the second phase. So we have different types of level design. So I can use a two-level factorials. That's saying for every factor, I'm going to look at the low and the high level of it. And default generator says that what I'm going to do is just use the designs that are available basically out of a standard textbook. Now, as you get more sophisticated, like at a Blackfelt level, you might do this, and then you might specify the generators because you want to control how the variables are used. Or you might want to do a two-level, and you want to fix different factors. And so, for instance, if you're doing a DOE and you're looking at agriculture, the ground doesn't change. And so you'd like to fix it, but you want to fix it by different locations because the ground doesn't change in those locations. So that's what a split plot design is. A Plackett-Berman design is where you're trying just to sort out and say, do any of these factors matter? So again, those are two-level designs. They're very bold in terms of how you choose the low and the high at the limits of performance. And the idea is if there's no variation seen across the low to high on a factor, it's not significant, we can eliminate it. And then the general full factorial design is a factorial design that we can use just the same as here, but it has its own approach, but we can use lots more flexibility in terms of what we do. So if we have different factors, so here we have 4 factors, okay? So we choose the factors. So the factors are standard rate, installer experience, travel distance, and service areas. So we choose 4. And then we can take a look at display available designs. So what Minitab does is says, here are the available designs for full factorials. So the green are the ones that give you a full factorial design. Reds do not. Okay, so if you remember resolution 3, here the main factors are confounded with two-way interactions. And that means mathematically you can't tell is there a difference in the main effect or a two-way interaction. For resolution 4 design, so there's a confounding between main effects and three-way interactions. So again, you don't know if it's a main effect or a three-way interaction, but more importantly also two-way interactions are confounded with each other. So you can't really tell if those are any differences. So we typically would like to have what's labeled a full factorial or resolution 5 or above. And that's why these are all selected. And what it says is, if I have 2 factors, so I have an A and a B factor, then I can do that in 4 runs. If I have 3 factors in 8 runs, and in 5 factors, it's 16 runs or 32 runs. So at 16, it's a resolution 5 design, and at 32, it's a resolution it's a full factorial design. So we're focusing on those that are labeled full factorial here. These are the easiest ones to analyze. Things get much more complex when we start having a reduced, if you will, level of design. So a half fraction or a quarter fraction. So a half fraction is taking the 32 runs to see all of the data combinations and then doing it in 16. So I'm doing it in half the runs. And it's too complex actually to try at a green belt level to teach you these ideas about the half fraction or quarter fraction or fractional factorial designs. So those are black belt level approaches to designed experiments. But here we can do the full level factorials. That says okay. So those are interesting to know. And then designs. So given the data that we have, I can either do the full factorial or the half fractional factorial. So we're going to do the full factorial. And then number of center points per block, this is something that we also get into at a black belt level, and number of replicates per block at the corner. So we're going to ignore the center points because that gets into a complexity that goes well beyond our ability to teach at a green belt level. And then the replications is how many times do I want to redo the experiment? So remember we have at each of the points in the hypercube a corner. So on a standard hypercube there are 8 corners. If I have 2 replicates, that means I test those corner conditions twice. So that means I will do 16 runs instead of 8 runs. So every time I choose a higher replicate, I'm going to choose that many more runs in a design. Okay? And so then I can just click OK, and it's going to give me a design. Now I don't want to click OK at this moment because what we see is we've already got a design. Okay, so we have in these different here, this is the design. It's the standard order, it's the run order, it's the number of blocks, and the number of center points. And what we see if we look at this, we see that we have, in each of these, there's 16 runs. So this is the full factorial. We see there's 1 block, that means the whole experiment is treated the same, which is the simplest. There's 1 center point, and that says that the whole experiment is really just in one location. It's not moving at all in terms of the center point. I have standard order and run order, and they're both the same for this experiment. Now, normally, standard order is randomized, and run order is how we do the experiment. But again, we simplified for a green belt level to show it this way. And so what we want to do is we want to input this design into Minitab so that Minitab will recognize the design. So we go down Stat DOE and Factorial, and here what we can do is define a custom factorial design. So if we input, we select this, we say, okay, what are the factors? So the factors are the different X variables that we're going to change and look at the low and high level. So standard rate is 1, installer experience is 2, travel distance is 3, and service area is the 4th. And so we want the 2-level factorial, so not any of the others. And then we come to high-low, okay? And now notice it's picked up the information about the high and lows. And it says that this data is uncoded. So if it was coded data, high would be a +1 and low would be a -1, okay? So this is uncoded data, so this is okay. And then we can take a look at the designs. So now these are sort of in a light gray, and what we see is order of the data. So we need to specify a design. So if I specify by column, okay, so standard order is standard order. If I specify run order, it's run order column. Oops, I have to click in the box first and then run order. And center points, I specify by column, click in the box and put center points. And specify blocks by column, and I put in blocks. Okay. And then I click OK, and now the design is registered. Okay. So if I click OK, now Minitab is thinking, I understand what's in the spreadsheet. And here I have the complaints, that's my Y value. Now, this is as far as we get in terms of this particular module. Because what we're going to do is we will come back in this next module where we talk about DOE in terms of the analysis of it, and that's the point where we put complaints in as the Y variable. So the idea is, now that we put this data into Minitab, we would actually go and do the experiments according to the run order. So we'll come back in the next module and we'll talk about how do we actually analyze and interpret the outputs of a DOE. Now I think you'll see that understanding how to get the data into Minitab is actually pretty important. And it's not necessarily straightforward. But once you get the hang of it, you'll see it's pretty easy to do. Now the next question is, how do we actually analyze that data to make some sense out of what the experiment actually did? That'll take us to part 2 of this Minitab tutorial.